Okay, it's restarted.
Okay, perfect. And yeah, this works. Present to external display. Okay, this is good. Okay, thank you for your patience. Sorry about the technical issues. So this week we're just gonna talk about autoencoder, which is a very important part of unsupervised machine learning, which is kind of left out from the Coursera platform uh, that's given to us in principle. And without further ado, this week we're gonna talk about autoencoder from three aspects and kind of just introduce it in a general form with a coding example. So first, we'll talk about the architectures, and by comparing it to the vanilla fully connected neural network, and by the comparison, we can easily see that why we decided to do the autoencoder and how it can help us in applications. And that leads to the second point, which is the application of autoencoder. And the first two parts kind of connected because those two are just from the architecture we can lead out the purpose. And the third one is just a simple coding example for to code out a really simple, I guess, a really simple autoencoder and use it for the denoising purpose of that. Okay. Denoising autoencoder is one of the main usage of autoencoder, and later we can see why. Next page. So, okay, so first we'll talk about the architecture of autoencoder. So on the left side here, this is a fully connected neural network layer, and the left side is the input and the right side is the output. Usually, we use this fully connected layer to reduce the dimension of our data. By reducing the dimension of the data, I mean is that, for example, you have how many input is this? 1, 2, 3, 4. You have 7 inputs here, but in the end, you only need 5 of that. Or if you want to do a binary classification, you might just need 1 output in order to, you just need 1 output to do the binary classification. So that means that we're reducing the dimension of the input from 7 to 5 in this case, and 1 in the binary classification case. And if you need more for regression, then you can do that. You can do that, or multi-class classification. So usually, for neural network, we're doing the reducing dimension thingy, just because if we go from the other end, we can also go from the other end, but that's just not like commonly seen. Yeah, this is the vanilla form. You can absolutely have low dimension and high dimension, but that's the whole purpose of autoencoder. Because on the right side here, this is an autoencoder, as we can see that it's kind of an hourglass shape. So the output has the exact dimension of the input, but the middle layer is kind of reduced. Its dimension is far less than its inputs and the outputs. And the purpose of that was, can we see on this side? So let's just say that we have an input of 28 times 28 times 1, which is just the common data set MNIST that we use to train. And so MNIST, the digit, the digit data set, it has 0 to 9 digits and with true labels, something like that. So for our autoencoder, we have an input of 28 times 28 by 1, which is grayscale, and it's a 1 color channel image, and it's passed to a convolutional layer So just notice that on the previous slide, I use a fully connected layer example on the right side here. But then here when we're talking about autoencoder, I kind of use a CNA example. It's essentially the same. There's not too much difference. It's just that every single layer before the fully connected layer, we're gonna after the middle part, the latent space, that's what we call the reduced dimension part. We're just gonna use the deconvolution functions in Keras to kind of just make how do I say this, to retrieve the dimension of the reduced data. So essentially, in the fully connected layer, since we're doing we're essentially just passing the low dimensional data to every single output neuron. But in the CN application, what we're doing is that we're essentially doing inverse convolution. But yeah. So in this case, let's just go through the autoencoder architecture again. We have a 28x28x1 input of the digit 2, and then we pass it to the first convolutional layer, taking convolutional layer. As we can see, that's more filters being created, and the image itself is being reduced to 14x14 and 7x7. The image is indeed getting smaller. And at the end, the convolutional layer become 3x3x128. Okay, so it has 128 and 128 filters. Sorry, channels. Each channel it have three. The partitioned image is 3x3. Okay, and this dimension data, this this convolutional neural network data outputs essentially flattened and passed to the neural network. This is a typical, so everything on the left side of the H, the latent space, everything before that was a typical convolutional neural network that we see. Yeah, there's really no difference between that, other than you can vary the dimension a little bit or do something else. Yeah, but then in this case, we have something else after we find out the flattened fully connected layer output, which is from the reduced data, we then again connect it to a higher dimensional fully connected layer. Here we denote by FC, and then we reshape it to the prior convolutional data and gradually restore the original pictures. You might be curious of why we're doing this. Like, it seems like we're doing useless work. But if you observe really carefully, we can see that the prior inputs on the left side here looks kind of different from the right side. And that's not counterintuitive, because essentially by reducing the original image inputs, we're essentially summarizing the main informations or main features about this image through the filters. And each filter it's reducing the size of the image. So essentially the latent space right there kind of have all the features of the image being summarized there. So it's the middle stage. You can imagine it as a layer that just have all the condensed information, condensed feature from the original inputs. And then by connecting again to the fully connected layer, we're trying to restore the original pictures. So by connected to a fully connected layer and do all the inverse convolutional operations, we're able to return the original, sorry, let me see, stage H called. It's usually called latent space in the middle. Yeah. Between the flattened FC. That's the latent space. Here, I think it just say that it's a H layer. So the latent space has all the reduced information, and then by doing the inverse convolutional, we're able to restore the original features as the inputs. But however, you can see that the two pictures is not complete. It's not completely the same. Usually, there's several ways to use this autoencoder. Other than the denoising example that we're gonna dive in deeper later, it's mainly used for just seeing that the prior reducing feature stage. So the first half of the autoencoder is truly working. So we want to see that whether the latent space truly have the condensed information from the input or not. Because if the feature is extracted falsely from the inputs, I guess the final outputs might not look something like this. It might just look like some noises or some like alien fonts or something like that. So that's the first thing. So usually usually for autoencoder, it's used for assistive training. After you train the whole autoencoder, the later part of the autoencoder is discarded. So we kind of just ignore this part and just use the first parts to make sure that this is the first part is correctly trained. And the outputs, we can use it as kind of like a visualizer of how the middle part is, summarized. However, we do have a more, a more considerate usage of that, which is denoising. So on the left side, you can see that the prior part is the encoder. The later part, it's called decoder, and it's an hour-shaped neural network. And in this case, it's kind of just repeated with the last slide, but I just want to compare again. The input and output image has a similar shape, but the edges are more blurry. But this is totally understandable, because if you imagine the first part of the hourglass as just extracting and summarizing features from the input image, that means that the image we don't see the exact information of the edges, the horizontal edges, the vertical edges. We kind of just know, okay, at approximately this position, we have an edge right there. It's more like that, because as you can see from the last page, previous. From the last page, the filter size is only 3x3, so it's impossible to restore all the information that we have for the original inputs. But that's why after the decoding part, the edges are getting blurry, just because it just doesn't have that much information to restore a high resolution pixel image. However, that's actually good for us, because by ignoring such intensive details about the input image, we're able to summarize some just general information about some area, about some main important regions, or some important edges of the original image. We're able to summarize the image instead of just copy pixel by pixel. So that means that if we add some random noises to the original image, so from the 3 given image, we can just vaguely see it's 4, 7, and 9. So how they usually do it is that they put some random digits on the, sorry, they put some random numbers on the original color information. So some of the pixels, for example, it was original black, and now it's just white pixel right now because we added the random noises, as we call it. And then from the corrected image, the autoencoder, what it does is that it summarizes the information of areas of this input image, and by summarizing, it ignored some of the minor details. For example, the noises in this case. So it's able to ignore the effect of the noises, or in another sense, it's not completely ignoring it, because sometimes the noises could cause some issues in the restored image. For example, some of the edges are breaked in the middle because the noise was too intense at that part of the original image. Something like that could happen. But essentially, the encoder part of the autoencoder is able to summarize all the information and therefore spread out the impact from the negative impact from the random noises that we have right there. And therefore, by spread out impact, and therefore from to some extent ignore the noises, we're able to restore the original image. And that's also the case of some of the common filter that we see right now in the market. So like I don't know, so for the Instagram filter or like the Snapchat filter, it's able to restore some of the old pictures of your family. So like this is essentially a really similar example of that. And if you have too many, like if your picture resolution is not good enough, we can also use the autoencoder to solve that issues. But instead of using the first part of this autoencoder, we're essentially using the second part of it, because we're inputting from a lower resolution to a higher resolution. So denoising was one of the most important application of autoencoder. And as we can see, it's a really flexible architectures, and the autoencoder as a whole we can use to assist our training. And by taking only the encoder or decoder part, we're able to summarize or extend the dimension of our input data. And therefore, we can do all kind of things like denoising and etc. And this is it for the slide. But I do have a coding example that I want to share too. That I really want to share. I was originally planning to code it out, but it seems like my laptop is not supporting me to do so. So I'm thinking to just share my screen, and so we can talk about the outputs of that. Because I apologize for the inconvenience. It's just yeah, I was planning out to just code it up, but it's my laptop is not letting me do it. It kicked me out once I share my screen. I'm sorry about that, but that's okay. You still get to see all the code, and I will make sure I go slow so everyone got a clear understanding of each line of the code, and we can also test out the code in the middle. Just to make sure. Let me see if the same thing. I would need the GPU, yes. Okay. Let's start from the just to make sure. Can you guys still see the screen? Okay, let me just stop sharing it for a second. I am screen sharing. I am screen sharing. Stop share right there. They have a couple of questions. Yes, you can ask them first, and then we'll go to the slide part. Yes. Why do you need to flatten before transforming to a latent space? So essentially, let me just share my, because we're talking about this, let me just share my screen again. Okay, it's perfect. I flatten it. You mean that we're summarizing from the flattened stage to the H stage, right? Yes. Okay. So this is why, because we kind of want a feature vector. So as what I just said, that usually in training the autoencoder, we want to kind of just discard the later part, because the later part is a way of us ensuring that the feature vector is it's really summarized correctly. So the H space is not only a middle stage for the autoencoder for them to be collected, but more importantly, it's kind of just a feature vector of the original image. So if you have understanding of RN, and this is kind of like we're creating a word embedding for a word, and this is we're creating an image feature vector that summarize all of the information of the original image in a really low dimension vector. That's essentially what we're trying to do. So instead of just using the original convolutional layer, because it's 3 times 3 times 128, and it's nearly impossible. Like it's really hard for us to tell whether our outputs is being created successfully, because by flattening it, by doing the convolutional layer, we're kind of summarizing it, but not really, because by doing the convolutional layer, we're extracting features using the different channels and different filters. We're doing that, but we truly need the fully connected layer in order to see out of those like extracted information. Just by the filter itself, it's kind of just vague and nearly impossible for us to see or classify it. By connecting it to a fully connected layer, then you have a lot more connections, and then reducing the dimension of a single of a really low dimension single feature vectors. And in that ways, we can easily classify the feature vectors, or just use some sort of regression, or to just see how accurate our model is doing. And by also reducing it to a really low dimensional vectors, we're able to ignore all of the details, as what we just said, as what we just presented in the denoiser. So the flatten part just means that we're making it into a really high dimensional single vectors right here. So it was originally 3 times 3 times 128. So here we'll just use 1152. So like we're just, instead of having the spatial information, we now convert it to a long vectors that kind of disregard that part of the information. Any more questions? Can I explain how convolution works? Yes, I can. So I can just go into my C slide. Okay. So convolution, it's really easy, because essentially what we're doing is that, for example, if we have an image like the green, and in this case we're not using RGB, we're just using either 0 or 1, so that it's really just like a pixel pixel diagram like that. And so here let's just say that yes, in the math intuition, yes, I can do that. So on the left side, the green image essentially is the input image that we have, and all of these entries either 1 or 0. 1 stand for maybe like the black pixel, and the 0 stand for the white pixels, something like that, or maybe green and red. So you can see that it's the information. Sorry, let me just can I annotate? Draw. So we can see that this part is kind of like in the shape of a slanted arrow, something like that. And the right side is the filter that we have to extract the information in each area. By convolution, it's really easy because we're just superposing the filters on top of the image and do the dot product. So if we maybe not dot product, it's just superposing the filters on top. Let me just see. Yes, we can do this. Something like this. And for each entry in the filter, for example, the one here, we're just multiplying elementary wise to the original image. So by doing that, we can successfully summarize the information of the image by the specific filter. So here we have one. So after we multiply everything, we're just gonna add them together. So left side is 1 and plus 0 plus 1 plus 0 plus 1 plus 0 plus 0 plus 0 plus 1. So that together adds to 4. And then we're going to move to the right and do this again. So by doing this, we're able to see that whether the filter fits with the image in each region or not. So like we can do, in this case, by doing the convolution, the image itself, the size might not reduce, but essentially we're just summarizing to some extent the information in the certain area, because in this case, the before we convoluted it, if we take a stride size, that means that how much we move to the right each time and to the after we done the convolution. So if we do a stride size as 1, that means that we shift 1 pixel per time we finish the convolution. We're gonna shift 1, 2, 3 times, and when we going down, we're gonna shift 1, 2, and 3 times. That's also 3 times. So after we complete the convolution, the input image will become 3 times 3, and that summarizes the original image along by the superposed filter. And let me just clear all my drawing. So why we need a filter, and I'm just gonna explain it for a little more. So this is how we can detect the edges, because yes, so this is how we can detect the edges. This is essentially an edge detector, just because when we're doing this, we're able to the middle parts, we're ignoring the middle parts and see if the left side kind of cancel out with the right side. And by doing that, we're able to kind of just detect the vertical edges in this 3x3 area in the original image. And by superposing that on the original image, we can see that the vertical edges, most of the vertical edges in the original pictures is being exposed. So that's the math intuition of the convolution work. So it's just superposing the filter and summarizing the information in a specific region. Any more questions? Okay, let's talk about the autoencoders code. Just copy it. I should reshare it to open up my Chrome. Yes, that's perfectly correct. So detecting horizontal edges will just be the second row of the filter is all 0, and on the top and the bottom will cancel out. So it's just 1, -1, something like that. Yep. My pen. Because sometimes it's just a matter of choices. It's just a matter of choices. Yes, I think you can use all -1 and 1, because if you want to put -2, that means that when we're summarizing the information, just on the top there, that specific pixel will be heavily penalized. So if the upper part and the lower part has high contrast of its value. For example, if the top is -2, the bottom is 2 for the filter, and for the input image, the corresponding pixel becomes maybe like 1 and 0. That means that that specific contrast, like by doing the elementary wise multiplication, the top part is going to specifically emphasize. And if the top pixel and the bottom pixel has a high contrast, that contrast is going to be specifically emphasized. So it's really a matter of choices. And also, if you if you want to detect like perfect straight edges, I think maybe -1 work. Yeah. By adding some like -2, -3, we can also allow some, I guess, uncertainties in our pixels, because even if the pixel was not so, straight, it can still allow some small slanted angle to happen. Because the information will still be summarized. To some extent penalize it, but it's still kind of preserve that kind of vertical information. Yeah. If you really wanted to know how it happened, I would actually encourage you to take the slide from the CN intro parts and kind of just repeat the convolution informations that I first introduced for, like have the green and the orange parts. So by doing that, we can see that you can actually see that the one part, when you summarize the region in that part, to summarize the pixel will have a significant like larger value than the region that is mostly empty. Okay, any more questions? Cool. Hope everyone can see my code. I'm just gonna go through this. It's actually not too long. It's just mainly it's just epoch training information, and the model information is really not too much. So the first and second parts, right? The first and second part, it is just library imports and from the TensorFlow, not too important. As we can see that we're using max pooling, dense layer, aka fully connected layer, and some convolutional, something like that. And then we're taking the Keras dataset from MNIST. MNIST is the digit data that we usually see, and from 0 to 9, yeah, something like that. So before retraining, we always do the normalization. So by doing the normalization, we kind of speed up the training process, and that's just what we usually do. And just because the MNIST data, it's kind of the range from 0 to 255, so that's why it's divided by 255, as every single RGB channel is up to 255, but this time it's just grayscale, so we just do not separate the channel and just divide it by 255, so that each digit we have, if we have 255, after we divide it, it will become 1. So we'll always have something between 0 and 1, which is easier for us to clip it or to trim it later. So then we do the reshape. So if we we kind of reshape the X train into something like the length of the X train, as well as 20 times 28 times 28 times 1. So we're creating our training batch as a whole. So if we print the X train shape, it will become 60,000 to 28 by 1. So that just means that we have 60,000 of training image, and each image is by the shape of 28 times 28 pixels, height and width, both 28, and 1 color channel. That means that we have a grayscale. Okay, any questions so far? And below, we're just doing the same thing for the testing data. Okay, so we have 60,000 of training data and 10,000 testing data. That is just what we said before. And below, the noise factor. Okay, the noise factor is kind of just a coefficient that we can decide a hyperparameter that we can use on our own to see how noisy do we want the data to be. So if we set it to 0.1, so if you look at the cell as labeled creates noisy data for train. If you look at that cell, we can see that we're essentially adding some random normal number from 0 to 1 to, sorry, maybe, yeah, it's from 0 to 1 to the original X-train data. But this 0 to 1 data is then timed the noise factor. That means that the higher the noise factor is, the bigger impact the noises can create to the original data. So it's just how noisy do we want our image to be, and this is set to be 0.5 so far. And below the X-train noisy is essentially we're clipping it to 0 to 1, because if we originally have 0.9, for example, and we add 0.5 to it, for example, that will become 1.4, but that's kind of against of what we did for the normalization step, and could create some sort of problem in our training. And that's why we use the NumPy clip to kind of clip all the noisy data and create an upper bound and a lower bound for it. And as we can see, our data is kept between 0 and 1. And printing that, we also need to do the same for the test data as well, such that both training and testing set, we have a consistent condition. So now we create a really easy encoder network. So first we have a convolutional layer of using activation functions of value and no paddings, and its shape is 32 channels, and each filter size is 3 by 3. 3 by 3 is mostly preferred in the market right now, because essentially a 5 by 5 filter is the same as a 3 by 3, just into iteration. So that's 3 by 3, and then we do a max polling to reduce our dimension size of the image. We do a max polling, and then we do the convolutional again to just convolute our max polling results, and then we essentially assign the outputs of this convoluted after all of those operation to put that in a max polling, and we name that as our encoded model. So encoded is our outputs, and by putting it the input image, which is the input, with the encoded, which is the output from the first part of the autoencoder, which is the encoder, we can create this specific model. And by putting the summary there, this is the first model. As we can see that the total number of parameter is 9,568. This is a relatively really small network right here. Okay, any questions? Okay, cool. Now, after creating the encoder, we're just doing exactly the same thing. And we do the decoder. So this is exactly the same, but essentially each operation was essentially just inversed. So for the convolutional 2D, we still do the 2D. We still wait. Oh, and each following wait, it's not inverse, is it? 2D. Oh, but the size is different. Okay, that's okay. So essentially, by doing the convolutional 2D, it extend the inputs of the latent space. So that's how it does the inverse convolution. Although I'm still kind of like hesitate on this, but okay. And then it followed by upsampling 2D, which is inverse of max pooling. So essentially, we're doing the inverse of max pooling, and each step is exactly the same. So in this way, we can create our decoder. And yeah, it's ready signal it. Parameter. So it's making the diagram rolling. So that's the decoder part. And then we're sequentially connected the encoder and the decoder to create our overall autoencoder model. So as we can see that here, we define our inputs as shape of 28 times 28 by 1, and encoded equals the result encoder, and decoder equals to the decoder model with the encoded result feed into it. So that's formally we connect our model, and then we define our overall model named autoencoder. And here's the summary of that. And overall, we have 28,000-ish parameters, and this is definitely a really small network, not too big. Yeah. And then we can do the training. So for the training here, we can see that this is really slow. Actually, it's not too slow because I turned on the GPU option. But here, essentially what we're doing is that we're using optimizer Atom and use binary cross entropy as our loss valuation functions. And then we compile our model using that, and then fit it. So as totally we run 10 epochs. That means that the training data is seen by the model 10 times, and each path size, each feeding size is 128, and we allow shuffling. So all the digits are kind of mixed together. So that's looking at the loss, we're reducing the loss. So it reduced from 16 to 11, like the training is indeed improving. Right. Okay, I thought you doesn't want me to screw that. Why this doesn't show set complete training? Okay, anyway. Okay, now it's done. So we can actually so now we finish up training. We want to see our essentially training results to see how well the denoiser has worked. So we want to see if the noises from the picture is truly eliminated. So the first thing that we do is that for the X test noisy, so we essentially put the first, we sample the first 10 pictures from the X test and feed that into our encoder. So, and then we take the encoded image of the summarized feature vectors of the input image and feed that into our decoder. So that by seeing the decoder shape, which is the last line of the terminal output, we can see that we essentially we recover the original input of the image. And last, we display the image. Yeah, as you can see, the input image and the output image is it's really similar. For example, for this one, it's almost exactly the same, right? But for some of the noises, we can't fully eliminate the impact. For example, like the 5 here. If our original noises kind of cut off the edges or stuff, that will actually reflect in our image, just because the impact is not fully spread, during the convolution process. We cannot fully eliminate that. And for the 9, because you can see that noises add a little bit more emphasis inside of the circular region of the 9, the outputs result is also a little bit blurred. So it's not perfectly recovered, but I think this is how well that the MS data can do. So for the 7, we can also see that the noise is too concentrated in the 7 below, like in the lower part of the image. That's why there's a little bit extra things there. Compare that to our original image. Yeah. Oh wait, no, this is our original image. Sorry, I made a mistake. The original image does have the little bits of I don't know, like a dots there. That's not belong to the 7. And in the noises part, it's our autoencoder kind of just see this little dot as one of the noises, and as you can see in the recovered image, the dot is completely gone. So that's a power tool of autoencoder, and this is just a denoising example of that. Okay, any more questions? That's all I have for today. Yeah, that's good. Okay, stop share. Yeah, thank you so much for coming, and have a good day, guys. Yeah, no worry.